Hi. In this short video, I want to give you an insight into transformation matrices and the parts that I find the most useful to know about. So let's get started to keep it short. This is a transformation matrix. It's a 4x4 table with numbers. So we have columns and rows. The columns are usually called also column vectors because you can look at these columns as vectors. And when you have an object that is in the origin, it has no rotation or no scaling, you will see that this is the way the matrix looks like. It has ones on the diagonals and zeros everywhere else. It is also called the identity matrix because it is not transforming points into another space. This happens as soon, however, when we are changing the location of the object, like here. And you see that the matrix is changing, but not in this 3x3 part here, but in this last part. And by the way, the last row can be ignored for now. This is useful for special things like projection matrices, but in most cases, this is the part that you do not need to take care so much about. So, what do these columns describe here? What you see in the last column here is just a vector, and we can visualize now the vector like this. So it goes from the origin to this point, because this value is the position to which this object is being transformed to when we apply this transformation matrix to this object. This is relatively commonly known because it's so easy to read. You just know this is the position. Very simple. What is a little bit less easy to read is this part. This is the rotational and scaling part. And this is exactly what I want to talk about. So when I rotate the object, you see that in this case, two columns are changing, the X column and the Z column. That's how I call them for now. And the reason is I'm rotating around the y-axis, and the y-axis is not changing. I can do this also with the x-axis, and then you can see that the x-axis is staying constant, whereas the other two columns are changing. And you may have guessed already, if I visualize this, these kind of vectors are describing nothing else but just the, coordinate space of this object. And now that you see all the values visualized on the matrix, you probably understand how the system works, because it's fairly easy to understand. If I scale it, it will only scale the y-axis part, so the second column of the matrix. And this is really relatively useful to know. First off, when you have a matrix, you can take a look on it and you can kind of figure out what it will do with the object. And this is useful when you're working with shaders and you work directly with matrices and you want to extract a certain property. Then it's useful to know that this is the way it works. And another part that is interesting to know is this more or less applies when the object is not scaled. The row vectors also encode something interesting. That is, when I rotate the object, it describes the counter rotation. So this is like the inverse, because if you transpose, that means if I rotate them, or if I mirror the matrix along the diagonal, a rotational matrix is being inverted. And that is, again, quite useful to know when you are working with shaders. But also in other cases, this is, I have found a few cases where this is being useful. For instance, knowing how this worked when building this gizmo object that I've programmed here to display and control this object, I made, I used this kind of knowledge to work this out and make this work. So I believe this is useful to know. And if you learn something, leave a like, tell me what you think, and hopefully I will make another such video about other such aspects which I find useful to know.